Okay, this will be the 7th lecture on Z-transforms, all coming out of Chapter 5. Today we're just going to talk about frequency domain interpretation of the transfer function h of z, as well as start looking at frequency response for discrete time systems. So let's begin with a frequency, the kind of frequency response or frequency domain interpretation. It's a frequency domain interpretation of our system function h. I'm going to derive this much like we've seen before for Laplace. I think we also did it once for discrete time as well. We know that the output of a system at rest in response to an input is just the input x of n convolved with the unit impulse response h of n. And if I do that by equation where I flip and shift the input rather than the impulse response, I would get a sum, and I could have that sum on some variable k. Let's let that go from minus infinity to infinity. I'll have my h of k, and I will have x of n minus k. I know that our definition of frequency in this class has been everlasting exponentials. And so when we talk about frequency response interpretation of a system, we're going to be looking at what happens when an everlasting exponential is applied to the system. So let's go ahead and let our input x of n be that discrete time form everlasting exponential, z to the n. So we know that this is a discrete time everlasting exponential. When I plug that in, I'm going to get my output y of n as being equal to a summation, right? K equaling minus infinity to infinity. We still have our impulse response h of k, but then when we put in x as being z to the n, we're just going to get z to the n minus k. And this can be simplified a bit. I can pull the z to the n term out front, so I get a z to the n. It's not a function of the some variable k, which goes from minus infinity to infinity, and then I still have my h of k, z to the minus k. Well, we've seen that sum before. If I take a look at that overall sum that's sitting there, that just looks like the bilateral z transform of the unit impulse response. I know that that is my h of z. So we get a really familiar kind of solution that comes out of this. We know that when an input, right, x of n being equal to some z to the n goes into our system, that is a linear time invariant discrete system, out pops an output y of n, which is going to be that same input, z to the n times h of z. An everlasting exponential in gives us an everlasting exponential out, modified just by the complex constant h of z, which is a function of the input frequency z. So what do we get? We could, if you like, write this in a slightly different way. We could sit there and say that y of n, right, is equal to x of n times h of z when the input x of n is equal to that everlasting exponential. Or, if you'd rather, we could come up with a different interpretation of our transfer function. It's a frequency domain interpretation of h that says it's our output y of n divided by the input x of n when, right, that input x of n is equal z to the n, something along those lines. So we get output over input when the input equals z to the n. So, frequency domain interpretation of h of z. H of z is a ratio to output to input. When we have a everlasting exponential go in, it is the gain factor of that everlasting exponential when it goes through the system. This is the basis of our frequency response idea. So, when we talk frequency response, right? Frequency response of a system. Frequency response. We know that we have some everlasting exponential that we talked about. Z of n is an everlasting exponential. Everlasting, need that to be a v, is an everlasting exponential. And if we wanted to talk about frequency in the typical way of sinusoidal frequency, we can restrict our z to the n to be on the unit circle, which really says r equals 1, right? And that is where, right? That one is where sinusoids live. So, frequency response. Traditional frequency response. This idea of frequency response, we could also think of it as being maybe a sinusoid response, right? Is our system function h of z when z is on the unit circle. Well, we'd seen before, z to the n, we'd seen before z is equaling r e to the j kappa omega. That's just polar form. So on the unit circle, right, is r equaling 1. That's just going to be e to the j omega. All right, I've probably made this longer than I need to. Frequency response then. Frequency response is looking at that complex constant, right, where sinusoids live. So frequency response is h of z, right, when, so given z equals e to the j omega, which I could write as h of ej omega, something along those lines. So frequency response, just like it was with our case when we were looking at continuous time, it's our transfer function evaluated where sinusoids live. If you do a little reminder, if you recall continuous time, the idea of frequency response was h of j omega, which was just the system function, right, evaluated where sinusoids lived in the s-plane along the omega axis. Discrete time is exactly the same. It's just our transfer function, h of z now, evaluated where sinusoids live, which is on the unit circle. Because this is a complex function of frequency, we oftentimes break it up into two parts. If I look at the magnitude of frequency response, h of ej omega in magnitude, that guy is called the magnitude response, right? And that is a real function of frequency. And then we can also look at the angle of h, e, j, omega. And that is called the phase, sometimes the angle response. If I want to show it slightly different, we know that frequency response, h of ej omega, can be written in a polar form, which is the magnitude response, magnitude h of ej omega, right, times e to the j angle, h of e j omega. So a little bit different representation of frequency response. Frequency response, right, is equal to a magnitude response and a phase response, coupled together in the standard polar form kind of way. Really, one point that maybe is worth making sense or comment here is that F response, the frequency response, right? Frequency response as a concept, as an idea, as something to compute, only makes sense it only makes sense if the system's region of convergence includes, right, the unit circle. Because frequency response looks at the system function on the unit circle, if the unit circle wasn't included in the region of convergence, we'd be looking at a place that it doesn't exist. That certainly wouldn't give us anything useful. You could calculate it, it just wouldn't give you anything useful. For causal systems then, this really says that the poles in the unit circle, right? If they're in the unit circle and it's causal, the region of convergence is outside those poles, then it will include the unit circle. It says that the poles are in the unit circle, right? Or alternatively, you could say that the system is stable. So frequency response really is a concept, at least for our causal kind of systems that we generally talk about, of being stable, those stable type of systems. It does provide us some information. So H of EJ omega, right, frequency response, provides information regarding sinusoidal steady state behavior, just like it did for continuous time. It's all the same. It's all about that steady state behavior. So, as with continuous time, if we have an input x of n being equal to just a cosine, so we'll make this a discrete version, cosine cap omega n, and we run that into our system, our LTID system, we know that the output to that system, and let's reinforce that this is a real LTID system. We can still get an output, it just won't be balanced in the same way as this, something we talked also about back in continuous time. The output is going to be the same sinusoid, right? So we're still going to get that cosine omega n. One of the things that's going to change, though, is its amplitude coming out. That's going to change based on the magnitude response. So I'm going to get a change in amplitude according to the magnitude response, which is a function of the frequency coming in. And we can also get a phase shift. So the angle of H, E, J, omega adjusts the phase of that cosine. You could prove it in the same sort of way, probably not worth our time to do so. It's exactly like the continuous time case, which we'd covered earlier in the semester. So we know everlasting exponential in gives us everlasting exponential out, modified by the complex constant h of z. Frequency response says let's look at that place where sinusoids live. So this x of z, z to the n, this everlasting exponential has a radius equaling to 1. That just gives us an e to the j omega. Those sinusoid pieces come out as sinusoids, and they're just modified in gain phase. There is a little difference with frequency response and continuous time and discrete time. So or maybe I should call it an important difference in discrete time frequency response versus continuous time frequency response. What is that difference? Well, let's look at the function e to the j cap omega. E to the j cap omega is a 2 pi periodic function. We know that. We've studied that before at the very beginning of the semester. So e to the j cap omega is a 2 pi periodic function. Because e to the j omega is a 2 pi periodic function, anything that is a function of that is a 2 pi periodic function. So frequency response, discrete time frequency response, h of ej omega is a 2 pi periodic function also. Periodic function 2. Now, for continuous time, frequency response, h of j omega, right, is not periodic, right? We don't get that same periodicity for frequency response of a continuous time system, but we do get a periodicity of a discrete time system. What does that mean? What does that idea of 2 pi periodicity mean in context of that h of ej omega? This periodicity, right, this periodicity is just reflective of the aliasing phenomenon, right? The aliasing phenomenon investigated earlier. So for example, right, if I have a cosine of 0n, that's a DC signal 1, right? We know that that is the same as a cosine 2 pi n, right? Because of aliasing. We had seen that before. So I could have a signal, right, that was DC, that I get samples of 1 with, DC signal coming out of there. I could have also had a signal, right, that was oscillating once per sample, something like that, and we'd also get those same values. So that's that aliasing phenomenon in there, right? We'd seen this guy before. Well, this is kappa omega equaling 0. This is kappa omega equaling 2 pi, if you will. And if we can't tell the difference in the signal that's going in, we're not going to be able to tell the difference in the signal coming out. That tells us that that frequency response is going to be 2 pi periodic. One of the nice things about this is that because it's 2 pi periodic, you really only need to plot, right? You only need to plot then the frequency response over that 2 pi interval. So since h of ej omega is 2 pi periodic, right? We only need plot or know, right? Or know this idea of frequency response, h of ej omega over a 2 pi interval. And we usually use what is called the principal range, that part that is normally not associated with aliasing, minus pi less than or equal to kappa omega, right? Less than pi, something like that. We include a 2 pi interval, and we usually use that one for what is naturally low frequencies. Okay, so another way we can see this guy is being connected to aliasing, or at least thinking about aliasing. Consider going from continuous time to discrete time. So I'm going to take some continuous time frequency omega, and I'd like to get the digital frequency kappa omega. So I could look at a particular signal, x of t, right, as being a sinusoid cosine omega t, and I'm going to sample at some rate, at a rate, let's call it cap f of s, the sampling frequency, being 1 over t, the sampling interval. So t is the sampling interval. Fs is the sampling rate. We'd already seen this kind of behavior before. We had looked up here, for example, of a sinusoid being sampled, right, every so often. Each one of these little intervals here is cap t, and again, cap t, right? We're just sampling once every cap t at a rate then. 1 over cap t rate is just 1 over the length of the interval. So if it was a 1 second sampling interval, right, 1 over 1 would just give me a 1 hertz sampling rate, or 1 sample per second, something along those lines. Well, when I do that, then I get a discrete time signal. So x of n, right, is equal to x of t evaluated when t is an integer multiple of that sampling interval. We already said that the continuous time input was going to be cosine omega, and we're going to replace now t with n cap t, which I could write as a cosine, right? And I'm going to have little omega cap t n, and we know that a discrete time signal's general form is kappa omega n. This tells us what the mapping between continuous time and digital, or the discrete time frequencies are. We can see that, right, cap omega equals little omega t. As long as we're sampling at a uniform sampling rate, right, we end up getting digital frequencies that are related to analog frequencies through the sampling interval. Okay, so let's do a quick review or look back at our z-plane. So if I look at my z-plane, I know sinusoids live on the unit circle, so there's my unit circle, something along those lines. At z equaling 1, I have my DC point, and at z equaling minus 1, that's cap omega equaling pi. That's my highest frequency, right? Now, if I want to think of keeping aliasing from occurring, suppose I want to prevent aliasing. I want to prevent aliasing in my sampled signal. How do I do it? What I need to do, a translation of this, is that I need to ensure my Fs, right, my sampling frequency, is high enough so that the highest continuous time frequency, let's call that omega max, right? That the highest continuous time frequency maps to some digital frequency, call it cap omega, which is less than or equal to pi, right? We've got to make it so that it doesn't cross that boundary of where the highest frequencies are. So what does that tell us? We knew that little omega t, right, was equal to cap omega. We know that that frequency, a digital frequency, right, must be one that is related to the analog frequency through the sampling interval. We want our cap omega to be less than or equal to pi. That tells me that I want little omega t to be less than or equal to pi. What is little omega? Well, and that's a particular omega, right? We want little omega max t to be less than or equal to pi. The highest frequency needs to map less than, right, the highest frequency digital. What is little omega max? If I put this into a Hertzian frequency, I know that little omega max, right, times 2 pi divided by 2 pi is going to be my Hertzian frequency. So omega equals 2 pi f, so omega max equals 2 pi f max. And I can get this expression as being 2 pi f max. If I want to do this in terms of Hertzian frequency, cap t needs to be less than or equal to pi. And that's kind of convenient because the pi's are going to be canceling from one another. What does that tell me then? It tells me that I can solve for my t, right? I know that t must be less than or equal to 1 over 2f max. Or if I want to do this in terms of sampling frequency, I know that fs, right, is equal to 1 over t. So let's just rearrange this inequality. I can bring the t to the other side through a division, divide both sides by t, and multiply both sides by 2f max. So that tells me that 1 by t, which is equal to fs, right, must be greater than or equal to 2f max. This is a famous result. So this particular result says what? It says that we can come up with some guidelines for how fast we have to sample an analog or a continuous time signal to avoid aliasing. We must sample at twice the highest frequency. There must be at least 2 samples per period corresponding to the highest frequency component. And that sort of makes sense, right? If you sit there and you think about some sinusoid going along, whatever the case may be, if I really want to capture something about that guy's oscillations, I better be able to get those peaks, right? I better be able to get something that tells me that that thing is oscillating along. 2 samples per second. So the limit, right? If I want to make sure that I'm not aliasing, I must be sampling at greater than or equal to 2f max. This is called the Nyquist criteria. This is the Nyquist criteria for sampling, or the Nyquist criterion, or the Nyquist condition. So as an example of this, just very briefly, right, quick example of this, suppose we're designing a discrete time system to process audio. You can think about this as being music, right? files. So the kind of stuff that we all listen to on our cell phones, whatever the case may be. Well, for us to think about how fast we want this system to operate, we need to know something about the frequency content of audio for humans. The human ear hears approximately, if you go across all people on the planet, hears from about 20 hertz to 20 kilohertz, something like that. So that 20 kilohertz, right? That 20 kilohertz is our F max. If you have higher frequency content than that, you aren't going to hear it, so we might as well not even include it. Almost all human audio systems, or when we're recording audio for humans, goes through a low-pass filter with a cutoff frequency of about 20 kilohertz. Get rid of any content that you can't hear, okay? And once we do that, we're ready to sample this guy. We're ready to encode it to put on our digital device. How fast should we be doing it? Our FS needs to be greater than or equal to 2 times F max. So how many samples per second we need needs to be at least 2 times F max, which in this case is going to be 2 times 20 kilohertz or 40 kilohertz. We're going to need to be able to do 40,000 samples per second in order to not alias high fidelity music for an audio system. If you look at something like CDs, for example, CD quality, when you take a look at what that thing is being sampled at, it's at 44.1 kilosamples per second, or just kilohertz is the typical way they'll say that. So CD quality is 44.1 kilohertz. What you'll see is that that's approximately 10% higher. That 10% higher just gives us a little buffer zone. It gives us a little bit of wiggle room for practical systems that aren't going to be quite perfect. So 44.1 kilohertz is exactly computed in the way that we would expect from the Nyquist criteria. So just a very quick example on that. So where have we gotten so far? Just a quick recap of what we've seen on this lecture so far. We were beginning this thing by talking about a frequency domain interpretation for our transfer function h of z. We showed that a input that is an everlasting exponential, that's this guy, right, results in an everlasting exponential out modified by that system function h of z. So this system function h of z, right, tells us the gain factor by which everlasting exponentials go through. If we take that everlasting exponential and we restrict it to r equaling 1, that's where sinusoids live. And sinusoid response is what we mean by frequency response. So since that gain factor, h of z, is how any everlasting exponential goes through, if I restrict it to sinusoids, I'm going to get my sinusoidal steady state type response, the frequency response. So taking a look at h of z, where sinusoids live, gives me this quantity that is called frequency response. From that, I can end up getting the sinusoidal steady state. Because it's a complex function of frequency, right? I have a magnitude portion, I have a phase portion. We typically plot those two separately. Just gives us an easier way to look at it. When I use that and I think about a sinusoidal input, right, I get that same sinusoidal output modified by the magnitude response, modified by the phase response. We noted that there was a primary difference between frequency response concepts. Up to this point, they've seemed very similar with what we saw in continuous time, but there is a primary difference between frequency response in discrete time than from continuous time. The discrete time frequency response, h of ej omega, and you must substitute into h the quantity e j cap omega. It's a 2 pi periodic function. For frequency response, continuous time, you took h of s and you let s equals j omega along the omega axis. That's where sinusoids is. Sinusoids live. That was not a periodic function. The periodicity was just a reflection of the aliasing phenomena. We went a little bit on tangent or off tangent to talk about that aliasing phenomenon a bit and seeing if we could come up with a strategy to know how fast we need to sample a particular continuous time signal in order to avoid aliasing. So we went ahead and applied a continuous time sinusoid. We took a look at the discrete time sinusoid that resulted in terms of that continuous time sinusoid's frequency, little omega, and we found that the digital frequency was related to the analog frequency through the sampling interval t. If we want to avoid aliasing, we need to make sure that whatever signal comes out has a frequency that does not pass that highest frequency point in the z-plane, that z equaling -1 or cap omega equaling pi. So we need to choose a sampling interval, a sampling frequency, if you will, such the maximum analog frequency, omega max, right, results in a digital frequency less than pi. If we make our substitutions into that, we get the Nyquist criteria, and the Nyquist criteria just says that you must always sample at least twice as fast, right, as the highest frequency that's present in your signal. Did a very simple example showing how this works with audio signals. Audio signals for humans go up to about 20 kilohertz, and so if we were going to represent that without aliasing, without getting those aliasing type errors where high frequency stuff sounds low, we would need to sample at least double than that. CD quality audio ends up coming in at 44.1 kilosamples per second, or 44.1 kilohertz. Satisfies that Nyquist criteria nicely. Okay, so what can we do? We can look at the magnitude response H, EJ, omega, and angle H, EJ, omega, right, to get insight into system behavior. The magnitude response in particular, right, will help us identify whether a system is low pass, high pass, or band stop. So let's look at a couple of ways that we can do that. If you have an H of Z, right, let's say in one particular case, suppose I had a system that could be represented as a Z over Z minus a half. Let's call that H of 1. And let's look at another system, H of 2 is being equal to Z over Z plus 1/2. These both seem relatively similar. The only difference is one little tiny minus sign in the transfer function for one coefficient. If I plotted these guys as pole zeros out, right, I'm going to go ahead and do that a couple of times over. So I'm going to draw my z-plane twice over. I always would like to give myself that unit circle for reference. Unit circles where sinusoids live. It's also the boundary for stability. Those are concepts that we looked at before. This first system has a 0 at the origin, right? And then it's got a pole at 1/2. The second system has the same 0 at the origin, but it has a pole at minus 1/2. So those are the pole zero plots. What do we expect behavior-wise out of these systems? In the first system, right, we see that the pole is closest, right? It's closest to low frequencies. And in the second system, we see that the pole is closest to high frequencies, So if you look at that distance, right, that guy closest there to high frequency, right? And in the first case, we have that little distance there, that short one, that's closest when we're near low frequencies. What was the basic idea of a pole? Poles are stuff, right? Poles are things that if you get a frequency near it, that makes the denominator small. That reciprocal nature then makes the overall gain large. Poles have an enhancing kind of characteristic. Poles want to make things larger. So this first system has a pole that's going to be boosting or enhancing low frequency, right? The second system has a pole that's going to be enhancing or boosting high frequency. If I was just going to guess, very quickly guess, something like a frequency response for this first system, what would I do? I'd go minus pi to pi. I know that I only have to cover the fundamental frequency range because it's a 2 pi periodic function. The same thing would be true for my second one. I would only be going from some minus pi to pi. And I would expect in this first one to have a higher gain near low frequencies than near high frequencies. It would be something that is more akin to a low pass like behavior. The second one would have something that would have frequencies that are going to get boosted. High frequencies are going to get boosted. So we would get something that is more high pass in nature. Nowhere would this response be 0 because there's no 0 on the unit circle. So just really roughly we can get an idea. Well, we can formalize this. We can use, just like we did in continuous time, the location of poles and zeros relative to where sinusoids live to be able to sketch out things like magnitude response and phase response. So again, and I'll just say, just like, right, continuous time, we can estimate magnitude H of EJ omega, right? And the phase response angle H of EJ omega by using by using our pole zero information. We don't have to spend a huge amount of time re-deriving all of this. I will just summarize the highlights of this. So again, we will write our function h of ej omega in factored form. And that's just as we did in continuous time, okay? So we could do something like the following. I could look at my h of ej omega, and we're going to be dealing with first, let's say, the magnitude response. If we wrote this in terms of some, let's back it up a little bit. Let's just show the details of part of this. So what would I have? I'd have my h of z being equal to, we know it's some b of z over some a of z. Instead of expanded polynomials there, we're going to factor them out. The first thing that we'd factor out on the top is just the overall gain constant. That's going to be b0. And then I'm going to have what? I'm going to have a product up to the total number of zeros, call them n, and I'm going to have z minus those zeros. So little zi is just the zeros of the system. And in the denominator, I'm going to have a product I equaling 1 to n of z minus the poles. So write this guy in factored form. We know frequency response says let z equal e to the j omega, and magnitude response says take the magnitude, all of that. So if I wanted to look at magnitude h, e, j omega and base it on this, I would get magnitude b0, right? And then I'd take a magnitude of a product, that's just product of magnitude, so that's going to be a product I equaling 1 to n of the magnitude ej omega minus zi over a product I equaling 1 to n of magnitude ej omega minus pi. What are these magnitude quantities inside these products? Well, each one of these guys, right, is basically a distance going from the pole or zero, right, to the frequency of interest, to that point e to the j omega, which lies on the unit circle. Exactly the same as what we saw for continuous time. It's just frequencies no longer lie on the omega axis, they lie on the unit circle. So I could write this in a more English kind of way, right? This is equal to whatever the size of that overall coefficient out front is, right? And then it's a product of distances, right? Distances from the zeros to whatever our frequency omega is, and I'm going to divide by a product of distances, right, from our poles to the frequency of interest, cap omega. Similar kind of way we can get the angle h of ej omega. It has exactly the same English that we saw for continuous time. It's the angle of that front coefficient, and because angles are found, at least from our polar form expressions, up in the exponents, and when you multiply those exponents together, the angles add, I'm going to have a plus the sum, right, of all the angles, right, angles from the zeros to the frequency of interest, and then I'm going to subtract from that a sum of all the angles, right, from the poles to the frequency of interest. Exactly the same as what we saw from continuous time. Exactly analogous to continuous time, right? What's the only difference? Looking at cap omega on the unit circle, rather than little omega on the omega axis. That's it. Sinusoids live in a different place for our discrete time. So let's go back at least to that first H1 that we did and see if we can come up with a really rough sketch. We'll do a more in-depth one a little later. So this first example again, let's go back and look at h of z in this particular case, and we call this H1 as being z by z minus a half. We had already sketched that pole zero out, right? So I'm going to go ahead and draw my z-plane. I'm going to put the unit circle there for reference, just like I always do. 0 at the origin, and I've got my first pole sitting there at a half. I would like to go ahead and get an idea of its magnitude and its phase response. So I'm going to start out with the magnitude response. If I wanted to take a look at that magnitude response, I'm going to go ahead and just draw a quick axis here. Unlike continuous, where you have to maybe spend a little more time thinking, what frequency range do I need to go over? It's always the same in discrete time. You're just going to go over that principal range, because if you cover that, you know everything, because magnitude and phase response, frequency response is a 2 pi periodic function. I only need to get enough points to be able to sketch in over minus pi to pi. So let's pick some easy points. Let's go ahead and look at magnitude h of ej0. This is the DC gain of the system. We see that this particular one has a B0 being equal to 1, right? So in this particular case, B0 is equal to 1. That gives me a gain of 1 there. And then I'm going to multiply that by the distance from the 0 to the frequency of interest. Frequency of interest here is at z equaling 1. That's my cap omega equaling 0. And since the 0 is at the origin, anything on the unit circle is going to be 1 unit from it. So the 0's distance to that frequency, or any frequency, is going to be 1. And then I'm going to divide by what? The distance from the pole to that frequency of interest. We can see that that is a half. So I'm going to have 1 times 1 over a half, or 2. This system is going to double, right? Double the input DC's strength, something along those lines. I could also look at something like the high frequency gain. So I'm going to look at h of ej, not infinity, but ej pi. Minus pi would give us the same value in this. B0 still has a magnitude 1. The 0 is still 1 unit. If you look at here now, we're looking at this high frequency point, right? The 0 is still 1 unit away, so we're going to still be looking 1 unit away. But now my pole is how far? My pole now has to go from 1/2 to -1. That's a total distance of 3/2. So I'm going to have here 3/2 in the denominator. Go ahead and do that calculation out. You get 2/3. So we had a DC gain, max for this system, maximum gain across all these frequencies of being 2. And we have a minimum gain, in this particular case, it's a simple system, of being 2/3. I've got enough now. I can probably get this guy all right. Here's 1, 2 units up. I know we're 2 at DC, and we are about 2/3, right, at pi. And that's the same as minus pi. Those are the same frequencies, right? Me coming across over here, pi, gets me the same way as if I'd come over here at minus pi. Same point in there. And if you look at this, in fact, because of the symmetry about this horizontal axis, we know that the magnitude response, all the distances there have the same symmetry across that horizontal axis. If I flip this guy top from bottom, it's the same. I'm going to get an even magnitude response, just like I did in continuous time. Real systems, those that have roots that come in conjugate pairs, will have the symmetry necessary so that the magnitude response is even. So I just need to sketch this in there, and I'm going to sketch it in a way, right, that I start out at that vector 2, and I go down to 2/3. Now remember, this guy is periodic, so it's going to pick back up and go back through this, right, something like that. It's a way of trying to get an idea, for example, that I would know not to try to sketch this maybe like this, because if I wrap that thing around, I'd get that sort of weird spiky piece, that sort of sharp edge. That's not likely going to happen on a system like this. We're going to want something that is, in this particular case, right, we want something that is going to be smoothly going when I go on that periodic extension, something along those lines. So I've got my magnitude response, doing just fine on this, and now I just need to worry about the phase response. So I'm going to, again, draw out my pole 0. I'm going to just give myself a little bit of a clean start with this guy. I'm going to go ahead and give myself that pole 0. There's my pole at 1/2, my 0 at the origin, and I would like to look at my phase response, so angle h of ej omega. Again, I only have to go over the principal range, so I'm going to go from minus pi to pi, something along those lines, and I would like to go ahead and calculate these out. I'm going to look at the angle response first at HEJ0. This is the DC angle. As long as it's a real system, I'd expect it to be one of two things. You can have a DC come through positive, or it might be negated, so that's a phase of either 0 or pi. In this particular case, we know that B0 was just a constant one that has an angle of 0 degrees. The next thing I'm going to do is I'm going to add in the contribution from all zeros. I'm going to draw this in red. If I go from that first 0 to DC, right, it's just pointing straight off to the right, okay? The angle that is making with the positive real axis is 0, so I'm going to get a plus 0 in here, something along those lines. If I go ahead and I think about the pole, that's the thing I'm going to subtract off, minus the contribution from the pole. That thing also just points straight off to the left to get me to that DC point, right? And in that particular case, the angle that makes with the positive real axis is also 0. And so if I add all of those guys together, I do get just indeed a 0. So I get 0, right, in this particular case at 0. I might want to do an intermediate thing here of angle. How about H, E, J, pi, the high frequency component. The DC term still has 0. Now the angle from both of these guys is pointing in the other direction. I'm going to have my 0, right, pointing to the -1 point, and I'm also going to have that pole now pointing off over there, same sort of thing. Both are making 180 degrees from the positive real axis, and so I will get a plus 180 degrees from my 0, and then I'm going to get a minus 180 degrees from my pole. That also comes out to be a 0. So I'm going to get 0 at plus and minus pi. Again, this kind of looks boring at this point. I'm probably going to need some more calculation points. I'm not going to do this with a calculator. I'm just going to do it sort of rough. Let's go ahead and pick up here this midway point between DC and high frequency. So I'm going to go ahead and look at the angle of H, E, J, pi by 2. DC value, B0 still has an angle of 0. Now I have to figure out the angle from the 0 to this point. This one I can do, right? The 0 pointing up to that guy has an angle that is 90 degrees. So in this particular case, I'm going to add in 90 degrees. And then I need to subtract off what? I need to subtract off the angle that is made from the pole to that frequency of interest. Now you could go through the geometry in that particular case. It's not horribly difficult, right? I know that this portion here, for example, is 1. This portion here is 1/2. So I could find something about this angle, right? This is going to be a 180 minus the arctangent of what? Opposite over hypotenuse. So that's arctangent of 2, something along those lines. I could go ahead and do that. I will pull out my calculator, see how well I can do this, hopefully get it to work out. So I'm going to take a 2 arctangent of that guy. I would like to convert this thing to degrees, since I'm keeping everything in degrees in here. And so I need to take that radian measure, which was 1.1071, and I'm going to take 180 degrees, multiply that, and then I need to be able to divide by pi. So I'm going to take 3.14 and divide those guys. That's about 63 degrees. So if I take through and I calculate this piece out, it's about 63. Whoops, got to get back down there. That's about 63 degrees. So let's go ahead and get that 63 degrees in there. 180 minus 63, right? That's going to be, this total thing here is about 117 degrees. Is that believable? Well, we can certainly see that it's more than 90, right? But less than 180. That 117 seems like a reasonable number. So I take 90 minus 117. That's going to be minus 27 degrees. So what am I expecting on my overall frequency response? Coming out here at pi by 2, I'm going to dip down, right, to some negative value before returning back up. And I'm going to do something similar going the other direction, but in an odd way. We know that phase response is odd, just like it was for continuous time systems. Magnitude response, which we'd seen before, right? This guy here was even. Okay, so we've got one simple example that we've done. We'll pick this up with a more complicated one here in a minute.